Hello, let's talk about Snowflake architecture. And no, this is not going to be a regular rant of storage, cloud service, and compute layer being the separate ones, because this architecture is suspiciously similar to what the engineers had already built in the 1980s and 90s. So I just want to understand, or at least want to explain that shared disk architecture was already into the industry. So what changes did Snowflake actually introduce while keeping the architectural patterns pretty much similar, but also implementing some things at core that make a very high overlap between shared disk architecture and Snowflake's architecture, and we'll also understand what the other architectures actually meant. So, which are typical the data systems architectures, I would call. My name is Srinivas Vishnupurikar, and I'm a Snowflake data and solutions consultant at Aries Data. So, let's get to the video. First, let's understand the oldest architecture, and then we will be moving towards the modern architectures. So this is the oldest architecture, on-premise monolithic architecture. So you can already see that everything stays within the local network since it is on-premise, and then we have storage and compute coupled together onto a single instance, meaning you don't have much scope for scalability, and even if you did, you would have to maintain a separate team for infrastructure that just manages the scalability, internal configurations, and so on. Besides, all of the legacy systems would essentially be migrated to the modern cloud alternatives. So again, this is not an architecture that needs much discussion on. Then we have this shared disk architecture, which is going to be the, I would say, a significant one in today's video, because this is something that Snowflake has actually revamped and implemented in a little bit of different flavor. So you can see that storage is centralized, but you have different clusters writing to the same storage. Now, what this meant was you had scalable compute. You could have different compute clusters with different sizes. In this case, for the simplicity, I have defined three clusters with approximately the same compute configuration, but we do have separation of compute and storage. Very good. So, what was the issue? The issue was increased disk contention and locking mechanism. So, locking mechanism is by far the most interesting concept that actually enables the acid properties that you study in OLTP systems. Note that these architectural talks that we are having in this video are not specific to OLTPs or OLAPs. Let's not get into that specificity. Here we are discussing about the data systems architectures. So it's a much wider umbrella, I would say, and I'm not targeting any OLTP or OLAP specifically. So let's understand what locking means. Locking simply states that if cluster 1 is performing some operations that is going to reflect some change in this particular data, we would call that cluster 1 has initiated a transaction. So a transaction initiates, and until this transaction initiated by cluster 1 is alive or is still in progress, these other two clusters like cluster 2 and cluster 3 are not allowed to access or at least deal with the same data points that cluster 1 is dealing with. So it's like a Mexican standoff where one cowboy is telling to the other that, okay, you agree to my terms and conditions, or I we have a shootout or a standoff. So that's, I know that was a very layman explanation, but the whole idea being every transaction that is initiated will end. No transaction is actually just started and left in the loop that never ends. No, every transaction ends, and either it is a commit or a rollback. If you have a transactional control language understanding, you will relate with this. And it does not matter whether your transaction is actually a success or a failure, as long as it maintains consistency. That should be the only thing uh, that should matter to you. And once transaction of the cluster 1 completes, which is either failure or success, cluster 2 and cluster 3 are uh, free enough or free to do whatever they want to do if they have to interact with the same data points as the cluster 1 was dealing with. That was the locking mechanism in the most layman terms. And then we have the disk contention, meaning the number of inputs and output requests that a particular hardware device can actually afford to serve. And in the older days, you had HDDs, and they didn't have really good contention strategies, or their limitations had some limitations, I would say. So these, although this achieved the separation of compute and storage, still not the architecture that would work really well at larger scale. Then we have shared nothing architecture, and this architecture is something that the older Amazon Redshift implemented. So let's say for a particular table, some data existed in node 2, 3, node 1, node 2, and node 4, and some rows existed in node 3 and node 5, or node n, let's say. In that case, if you had to perform certain complex operations like joins or group bys, or even filters for that matter, you would have to shuffle data into all of these uh, nodes, which is the core of the distributed computing, I would say. And again, that was, I would say, this is still a distributed architecture, but again, shuffling data between different nodes in a cluster is not an easy thing to deal with, and generally there is a lot of networking overhead, a lot of data transfer that happens, which is not very cost affordable also. So again, the architecture did work, but not the best one, what I would call. And again, this no Amazon Redshift actually came up with a newer architecture that uses the RA3 architecture, and it is pretty much the separation of I would say storage and compute, not at the node level. So in this case, we have each node having its own storage and compute, but I think the RA3 architecture is pretty much similar to what Snowflake did. So centralized storage and separate compute. Now here comes the hero of our video, which is Snowflake's architecture. So if you observe very carefully, the storage is centralized. Then we have scalable compute resources as well, as in different clusters that have been configured over here. So what's the difference apart from this network layer and the cloud service layer? The cloud service layer is simply that is managed by Snowflake itself, and depending on who your underlying cloud provider is for your Snowflake account, be it AWS, Azure, or GCP, the cloud service layer is configured automatically whenever you are creating a Snowflake account. That's the basics. But that is not how Snowflake's architecture actually solves the problem of contention and locking. So remember, contention was something related to the disk specific, which is what we would call the hard drive disk limitation. So that was completely eliminated the moment we introduced cloud services in this. So your Snowflake account is hosted on a particular cloud provider's account, be it Azure, AWS, or GCP. In that case, your underlying storage layer would be ADLS Gen 2, AWS S3, and Google's GCS, respectively. And now you know that ADLS Gen 2, Amazon S3, and GCS are highly scalable. So, would you ever worry about contention that happens underlying? Absolutely not, because at scale that is managed by Snowflake and the underlying cloud provider. And now the most important thing, the locking one. The locking happens only when two separate, let's say, two separate clusters are fighting for the same resource on this particular storage. So let's say cluster 1 and cluster 3 wanted to deal with a particular data point. Let's say cluster 1 was updating that data point and cluster 3 was reading from that data point. But okay, unless cluster 3 or cluster 1 is has either completed the updating the data, whether it is successful or failure, cluster 3 might not be able to read the most I would say consistent state of that particular data point. So that's like two separate clusters fighting, literally fighting for this particular data point itself. But in Snowflake's architecture, that never was an issue, because Snowflake operates on two major things, which is implementation of micro partitions, and second is the copy on write principle. So in simple terms, micro partitions are simply the chunks of large data sets divided into the smaller chunks, which lie anything from 50 megabytes to 500 megabytes. This is actually stated in on their official documentation as well, so you can clearly refer that. But the copy on write principle actually eliminates the need for locking mechanism in the first place. So let's understand how. Whenever you create a particular micro partition, let's say uh, this particular pink box is a micro partition. Let's name it MP1. And now multiple such micro partitions, let's say, constitute to a creation of one table. So let's say micro partition 2, 3, and 4 mean that we are with the table. Let's uh, table orders. So change its color to black. Perfect. So whenever you think that okay, certain data needs to be updated in micro partition 2, you would think that okay, this particular compute resource will update this particular micro partition, but that is not the case. In that case, your micro partition, this particular micro partition will be copied. So let's say let's change its color to light pink, and this light pink will only be updated while all three of uh, these uh, micro partitions will stay consistent. So now this is your updated table. If you notice that MP1, MP3 and MP4 have not been recreated, the only micro partition that was recreated was micro partition 2. Now this is the older version. Let's say out of 100 rows from these in this particular micro partition, only 10 were updated. In that case, this micro partition is just an exact replica of this particular micro partition, and let's say micro partition V2. For simplicity, this is the V1, which is the older one. 10 rows have been updated due to an DML operation, and now this micro partition 2 version 2 is now being made as an active micro partition for this particular table. Okay, so essentially this is the copy on write principle. You create a copy of a micro partition and then make changes to it. So when there is no particular micro partition or a data point to fight for, will there be a need for these compute resources to fight? No, not necessarily. Because again, when you can create as many uh, micro partitions as you want, and this is not something you create on your own, this is something that Snowflake does internally. So this is by far the most I would say the smartest implementation of how shared disk architecture can be revamped into much more scalable at large scale. And it's just amazing how engineers come up with these ideas. So yeah, the shared disk architecture can I would say Snowflake just revamped the shared disk architecture by the implementation of micro partitions and copy on write principle, where copy on write principle states that you don't fight for a particular micro partition. So two separate compute resources don't fight for the same micro partition. Whenever you want to update, you just create an independent copy, and then that particular micro partition will be the older micro partition will stay as it is, but the newer micro partition will reflect the changes that were supposed to be reflected in the older one. So that's the basic principle, and yeah, that's pretty much it. I don't want to make this video really long, that just wanted to share that despite keeping the architectural patterns similar, engineers can come up with some clever solutions and implementations. That's it. This suspicious similarity was filled with a lot of curiosity, and I hope you guys have liked it. And yeah, thank you very much, and I'll see you. Bye bye.